In this lesson, we're going to talk about two different special types of exponential equations. And one of them is doubling and the other one is half-life. And just note that when doubling, we know that this is growing by 100%. And when it's a half-life, we know that it's decreasing by 50%. So that's why these are special type of exponential equations. So in an exponential equation, if we had the doubling as 100, we would have 1 plus 1, because 100% written as a decimal is 1, which just simplifies down to this 2. Okay, so and then because we're talking about how long it takes to double, we want to think about it's not just the input letter, but also the length of time that it's taking this situation to double. Now remember, what's in the parentheses is called a factor, but now we also have to account for the time between the initial value and what's asked for. So what's that time period? And the time it takes to double. And then we also have this thing called the rule of 70. It will give us a percent, or it also give us how long it takes to double. And we'll look at it in all these examples by looking at this problem here. In July of 1953, the U.S. population was 60.2 million people. And in July 2011, the population had doubled. So in order to answer this question, by what factor does today's population increase? And factor means that I need to know the time between the initial amount and what's asked for, and I need to know the time that it takes to double. So the time that it takes to double, we're going to do that one first. So we know that it doubled in 2011, so 2011 minus 1953 is going to give us 58 years. And the time between 1953 and today, which is 2023, is 70 years. All right, so in order to answer this question, we're going to take 2, looking at our factor calculation here. So 2, and then we're going to raise it to how long it's asked for. So 70 divided by 58. And again, if you're using Desmos, we're just going to type in 2. And then we're going to use our fraction button, a to the b. And then 70 divided by 58. And we end up with 2.308 and so on and so forth. And remember that the numbers inside of our parentheses, so anytime we're writing these numbers in parentheses, we like to write them with 3 decimal places. And so the factor would be 2.308 is the factor. Now, what is today's population? So we're going to use the entire doubling equation. So the population is going to equal the initial value, and our initial value is 160.2 million people. This time we're doubling, and we want to know what the population, if this trend continues. So today's population is 70 years out, and it doubles every 58 years. And if we type this in, we've already done the first part, but we'll just type it in again in terms of 160 times, 160.2 times 2, because it's doubling, raising that, 70 years is for today, divided by 58 years for it to double. We end up with 369.81 million people. All right, so now we want to do some guess and check, where we want to figure out when 400 million is going to happen. So it's got to be after 70 years. So I'm just gonna guess, let's try 80 years. And so I'm gonna go over and I'm gonna edit my 70 and just make that an 80. And I have 416.75. That was a little too much, so we know it has to be more than 70. Now it's got to be less than 80, so let's just try 75 years. And again, going over to Desmos to calculate that, we end up with 392.58 million. So we're close. We need a little bit more, so let's maybe just 76 years. And when we calculate 76 years, we get 397.29, or actually 397.3. That's very close. So 397.3 million. Not quite at 400 million, so let's try one more guess up. So let's try 77 years. And when we do 77 years, we end up with 402.07 million. So it's either 76 years or 77 years. Well, if we subtract here, this is a difference of 2.7 million. And here we have a difference of 2.07 million. So 77 years is our guess. Okay, so now let's look at a couple other things that will happen. We want to find, okay, so here we're going to use this rule of 70. So by what percentage can we approximate the growth by? And it says use the rule of 70, because the rule of 70 will give us the percent if we know how long it takes to double. So our double time is 58 years. And so the rule of 70 is going to say the percent equals 70 divided by 58. Now, when we do this, we actually get the percentage as stated. We don't change it to a decimal or anything. So it's just 70 divided by 58. So our percent is 1.2%. Remember, percentages are in one decimal place for this. So 1.2%. So now we want to write an exponential equation using our percent that we know that's happening each year. And then answer the question what the population would be. So, so let's say, so this is, let me rewrite this to say percent and not just P. And then, so the population will equal the initial population, which was 160.2 times 1 plus, now we're going to use this percentage, so 0.012 raised to the y power. And so we're going to do this for 70 years. 1 plus 0.012 to the 70th power, which equals 368.77 million. And notice that we had one answer. We had the doubling answer, and we have the exponential answer. And actually, the doubling answer would be a better approximation of today's population because of the fact that the information was given to us in terms of doubling. And then we did a calculation 70 divided by 58. We rounded this percent. This percent as a decimal is rounded. So this answer has actually been rounded once already. So that's why the 368.77 million is a little less accurate than the 369, just based on how the question was written. Now, one more thing we want to look at is, so this graph is showing the population growth as a percentage. So what's our percent growing from over time? And so it's pretty held steady around 1% over time, but it's drastically decreased in the last couple of years. So if today's natural increase is 0.12%, we want to find out what does that mean in terms of the time to double. So the doubling time, again, is using the rule of 70. We can use it for two different reasons. And so now we take 70 divided by 0.12. Remember, we don't change our percent to a decimal when we're using the rule of 70. 70 divided by 0.12 means that it would be 583.33 years to double, beginning with year 2023. A couple of other scenarios. The number of deaths due to COVID from April 4th to April 10th, April 10th to April 21st. We want to calculate the percent growth, so we're going to use the rule of 70. So this is 70 divided by 6 days, and that's going to tell us what the percent happened in terms of it doubled in 6 days. And so that meant 11.7% daily growth rate. And here our COVID cases doubled in 11 days, so 70 divided by 11 days, because that's the doubling time, was an increase of 6.4% daily. So that's another way we can look at using the rule of 70. Here's just if prices, so we talk a lot about inflation and what's happening just in terms of the economy. So if prices increase at a rate of 4.5% monthly, what is that annual rate? So remember that we have 1 plus 0.045, and this is happening monthly. We want annually, so we're going to raise this to the 12th power because that's how many months are in a year. And we're going to end up with 1.696. And remember that 1 represents 100%. So all we're looking at is this portion of our situation. So we know that 69.6% increase per year. So what's the 5-year factor? Remember that the factor is everything that's in the parentheses. Okay, so a factor is all of this. So that's what a factor is. We want a 5-year factor. So we know the monthly factor is 1 plus 0.045. We want a 5-year factor. So we're going to take 1 plus 0.045. That would be a monthly factor. For 5 years, we want it to be 60 months. So 5 times 12 is 60, which gives us a factor of 14.027 is the 5-year factor.